All right, so let's talk about filtration. So, filtration, first of all, only occurs in the renal capsule. So, it only occurs within the glomerulus to the Bowman's capsule. Okay, so basically, we have about 3 liters of blood in the body. But it's circulating, right? So, in a 24-hour period, our bodies filter about 180 liters of blood into Bowman's capsule. Huge. Phenomenal, right? So I drew my little picture here. We know we have the glomerulus. Here, the efferent arteriole, afferent arteriole, and Bowman's capsule into the proximal convoluted tubule here. So how does stuff get filtered into Bowman's capsule? Well, if we review how things work in a capillary. And if you remember, this is from, the vessel chapter where we talked about pressure. And if you remember, you've got blood coming into the capillary, and it comes in at a pressure, basically blood pressure. And when it gets to the capillary bed, of course, the blood pressure isn't going to be, 100 and something millimeters per mercury. It's going to be pretty low because capillaries are small and delicate. So it comes in at about 32 millimeters per mercury, and we call that hydrostatic pressure. And that comes from the heart. Okay, so we know that the blood enters the capillary at 32 millimeters per mercury, and that pressure is putting pressure on the walls of those capillaries, right? So those, the capillaries are one cell layer thick. So what's happening in there? Well, stuff's getting pushed out. And as the blood goes down the capillary bed, that hydrostatic pressure gets less and less. Over distance, from the heart, it started at 180 or whatever millimeters per mercury, and then as it got down through the arteries and to the arterioles, it got less and less and less as it got further away from the heart. So as it flows through this basically straight capillary bed, it's going to get less there as well, from friction, whatever. So we know that stuff is pushed out with that, and we call that bulk flow. So that was just stuff that was pushed out due to this pressure on the walls pushing out fluid and stuff with it. That's basically filtration. That is filtration. So we also knew or saw that, we couldn't have all that fluid going out into the interstitial space and then staying there, or we'd blow up like a balloon. So there was a counter pressure, and that was osmotic pressure. And that came from the plasma proteins. Okay, so colloid osmotic pressure. And it was about, 30 millimeters per mercury, a little bit less than hydrostatic pressure, but it doesn't dissipate. It stays the same. Okay, it doesn't change along that. So that brought some of that fluid back into the vessel. And then, of course, at the end, in a 24-hour period, we had basically a net filtration. So stuff that stayed out in the interstitial space of about 3 liters per day, and that was handled by the lymphatic system. So that should be reviewed. We understand that. Well, the same thing is basically occurring here, or something similar. So we have blood coming in through the afferent arteriole into the glomerulus. And there's going to be pressure there. 32 millimeters per mercury. Basically, the glomerulus is just a fancy or a different capillary bed, basically. So we have that pressure of 32 millimeters per mercury coming out into Bowman's capsule. Okay. But just like in the other vessel, there's also the osmotic pressure that is countering it. So the osmotic pressure of about 30 millimeters per mercury. So that counters it, right? So that means things are being pushed out and then going right back into the glomerulus. All right. There's also, this Bowman's capsule isn't empty. Okay, it doesn't have nothing in it. It has fluid in it. So there's a pressure coming from that as well. So that's pushing stuff into the glomerulus, and it's about 15 millimeters per mercury. So this is coming from the fluid pressure within the capsule, within Bowman's capsule. Okay, so that doesn't really make for a very good filtration thing, because more stuff actually is going here into the blood, into the glomerulus, than is coming out of the glomerulus into Bowman's capsule, and we want that to be reversed. So if you look at this sort of anatomical way I've drawn the afferent arteriole, look how much larger this one is. That isn't a mistake. Okay, this is way larger than the efferent arteriole. So that means more blood can come in here than can leave. Okay, so that in itself is going to create a pressure. If you have, something like a big box with a big, with the top open, okay, and you're throwing things in it or putting stuff in it, but the only way to get the stuff out is a tiny hole in the bottom, it's going to accumulate more than it's going to be able to leave. Okay, so it's going to cause a pressure here, and there's going to be pressure on the vessels in the glomerulus due to the fact that there's just more blood in here and it's not able to leave as quickly as it came in. And that amount, which is going into the capsule, ends up being about 23 millimeters of mercury. And that's from the afferent arteriole, or the condition of the afferent arteriole being larger. So adding all of this together, we end up with about 10 millimeters of mercury. So 10 millimeters of mercury of stuff that's going into Bowman's capsule. And that is the filtration. So that 10 millimeters per mercury, that amount going in there, is the net filtration. So that is what we call glomerular filtration rate, or GFR. And this GFR number is important for the homeostasis of the body for filtering the blood. Okay? So the next video, we're going to talk more about this glomerular filtration rate, but this is how it occurs. These are the pressures that are created here that cause stuff to actually be able to be filtered into Bowman's capsule.